So our next speaker, besides being a fan of Stan, which we clearly like at this conference, she also loves loops. She loves loops in R, which some of us might be scared by, but if you do them right, they're not necessarily slower. They have a bad rep, but if you do them right, they're not necessarily bad. But she's also a fan of loops in music. And she even has a looper to put her voice over her recordings, and the looper's name is Lupita. So, everyone, please welcome to the stage Mayarí.
Hi, my name is Mayarí, and I also go by May. And I'll be talking about my experience handling the missing data of a randomized control trial with Syrian refugee children using tools in R. So first, I'm going to give you just a little bit of context about our study and the challenges that it presented us. Then I'll do an overview of the method that I use. I'll explain some of the tools and strategies that were helpful to navigate the main challenges. And then I'll illustrate the implications of missing data on some of our results. The International Rescue Committee and NYU Global Ties for Children have conducted several trials to test the impact of a program for displaced children in conflict-affected regions. And the program basically offered support for their academic and their emotional development. And one of those trials was conducted in Lebanon with Syrian refugee kids, which is the data that I will be telling you a little bit more about today. The study relied on survey data, and it involved different assessments that covered multiple aspects of the children's circumstances and development. And there were 3 waves of data collection. The goal was that these data could cater to multiple research questions and analysis that would contribute to our understanding of these programs and of these children's development in a comprehensive way. But these populations are fairly different from those that have been used in the past to generate most of the evidence base that we have about child development in the Western world. And so the education and child development experts at NYU aim to cover all possible ground in terms of collecting background information. It's also worth noting that this is a context where rigorous data collection is very difficult to implement due to security threats, due to the children's migration patterns, and also due to the lack of ID documentation for tracking them. So we ended up with over 900 potentially relevant items to account for, of which over 800 had missing data. And one of the first challenges is, how do we leverage all of that potentially relevant information in a context where we know so little and for which we may have culturally inadequate biases? And so we want to have a way to also reflect in our final analysis how cautious we should be about our results due to the missing data. And data quality also varied across different features due to volatile circumstances in the field. And on top of that, we had items at the site level, at the teacher level, and at the student level, as well as a bunch of items that depended on skip logic or had weird applicability dependencies. All things that can make addressing the missing data a little bit less straightforward. But why is missing data even a problem? When we have missing data for some participants, there is always a very good chance that their data is missing because of important differences between people, which can cause people that face specific circumstances to be under or overrepresented in our results. So basically, the results risk being biased. But also, data is usually costly to collect, right? And if you leave out the incomplete cases from your study, you'll be throwing away very valuable information. And if we're going to burden vulnerable populations with lengthy surveys, on top of the financial cost, we also have a moral responsibility to make the best possible use of their data. Okay, so to make sure that everyone has a sense of what's going on moving forward, I'll do a quick overview of the method that I use to address the missing data. And first, if this is a new word for you, imputation basically means creating predictions or best guesses for the missing information. There are many ways to go about imputing, and my choice was multiple imputation through chained equations or chained models. I think chained models makes more sense. This approach basically allows us to use all the available information from each participant to build a predictive model for each variable that has missing data, and to create an educated guess that is powered by your data of what the unobserved responses might look like. So for a second, let's just pretend that we have a super simple data set with only a few variables, and the red cells indicate missing information. So we start by filling in random starting points in place of the missing values, and then build a model for any one variable, say income. And this replaces our missing values in income with something that is better than just noise. And then we can use all the available information and our income variable with imputations that are already better than noise to build a predictive model for another variable. And now, instead of missing values, we have better than noise predictions for two of our variables, and we can build a model to get even better predictions for a third item with missing data. And so we get to a point where we have educated guesses for all the missing data, powered partially by noise, but partially by all the observed information from our data set. And we can keep on improving these predictions by iterating this process using better and better predicted values in place of the missing data. And that is basically what we refer to as chained models or chained equations. So where does the multiple part in multiple imputation come from? It comes from repeating this full process multiple times, but starting with different noisy values that could lead us to end in slightly different places. This results in us getting many different completed data sets with different final predictions for the missing values. And I think it helps to think about them as all the possible universes that we can imagine given what we were able to observe. But let's go back to our real-world data and its challenges. If we're using the mice approach to deal with the missing data, and we want to stay humble on what we don't know about a new context, then we may want to allow for the possibility that any of the features that our experts thought to collect data on could play a role in predicting any one variable or in explaining why some of its information is missing. But this implies building very costly models that account for tons of features. And then we'd have to feed those costly models for the hundreds of variables that have missing data. And then, because missingness rates and data quality varied across items, you may also want to iterate for as long as it takes the last variable to converge. And also, you may want to make sure that you produced enough imputed sets to get a good estimation of the uncertainty for all the variables that will be used for any analysis. But all of this is super computationally costly and time-consuming to run. So one of the strategies that I found helpful to reduce time and resources with no apparent loss in the quality of the imputations was to simply do a little bit of feature selection before imputing. Specifically, I found the Boruta package helpful. This is a wrapper of the randomForest method, which most of you are probably familiar with already. If you're not, just know that randomForest is a machine learning algorithm that you can use to build predictive models without having to make a bunch of assumptions about the functional form that relates the predictors with the outcome. It also rates the predictors' importance, and the Boruta package uses the importance scores produced by randomForest not only to rank the features, but also to help estimate which ones don't really add any predictive value. The general idea is that it creates fake copies of all the variables, but with their values all shuffled, so that the fake copies are just noise features with no true predictive value. Then it lets randomForest score the importance of both the real and the fake features. And by comparing the importance scores of the real variables with those that we know to be purely noise, it gives us suggestions of which variables should be accepted or rejected as having any predictive value. But there is a catch. Like most feature selection tools out there, you need to feed it complete data, which at this point you still don't have, because that's exactly what we are trying to address. So the practical get around that I used for these was just to fill in the missing entries with noise. Then run Boruta with each variable that had missing data as the outcome, and also run Boruta with non-response indicators as the outcome. So we can take into account the features that are related to the probability of missing that information. And then I just took a conservative approach when discarding predictors. I flagged for any one variable only those that came back as completely useless, both to predict the variable itself and the probability that it's missing. Here, for example, you can see which of the features on the x-axis were found to have no predictive value for the items of math assessment. Green indicates the count of math items that a feature had predictive value for. And so you can already see how by leaving all these uninformative features out from each model iteration of the math items, you'll save resources. The software tools that I found most helpful to implement multiple imputation were the well-known mice package and miceadds, which complements a lot of the functionality of mice. Some of the appeal of these packages is that they can handle mixed types of data and multi-level imputation, which allows us to get predictions that are consistent when we had missingness at both the teacher and the student levels. They also allow for a good amount of flexibility and control over what goes into the models. Our data also had a bunch of applicability restrictions and skip logic patterns at both the teacher and the student levels. And the flexibility of these tools helped us prevent predictions from happening where they shouldn't be happening. Also, these packages offer several options when it comes to choosing the types of models that you want to feed in each iteration of mice. I decided to go with randomForest because it's significantly faster than linear models. It naturally accounts for interactions and nonlinearities. It prevents us from making too many assumptions about the data generating process in a culturally different setting where we know very little. And it is also consistent with the feature selection process, which is nice. One of the ways in which mice offers flexibility is the control that it gives you over the predictor matrix. There you can make a bunch of specifications of what goes into each model and which variables are at what level of nesting. And before getting started, you can automatically use the flags from your feature selection process to populate the predictor matrix. And you can exclude a bunch of features that are unhelpful for each variable that will be imputed. It was also helpful to create objects that indicate applicability dependencies. I used those to automatically create interaction terms and populate the predictor matrix. And this ensured that all the applicable items for each student could be used to power the imputation models, even when applicability varied across students. Another object that helps complement this functionality is the where matrix, which allows to specify areas of the sample for which imputations are not applicable. And then there are the objects that allow you to specify how to model each variable. The meth vector is where you should specify the method that should be used for the lower level items, or the student level items in our case, or where you specify which variable is a level 2 item or a teacher level item. Or you can also specify if a variable should be passively imputed. And then the imputation function list should contain the modeling approach that you want for only the teacher level or level 2 variables. And lastly, for those teacher variables, the clustering ID needs to be specified as a list in the cluster bar object. And once you have carefully populated all those objects, you can run mice and get a bunch of the parallel universes that are possible for your data. We produced 100 to be safe. I'm not going to dive into this, but just know that after you're done imputing, you would have to make sure that your imputations are converging and blending properly. And you may want to check that there are no obvious lingering differences between respondents and non-respondents once you have conditioned on all the relevant features. And then you'll be ready to do your analysis and get a better sense of the role that missing data played in the conclusions that you can draw from it. Here I'm showing you the estimated average treatment effect on just 4 of our outcomes after we pulled the results we got from the different imputed data sets, where here our credible intervals already reflect the uncertainty brought in by the missing data. And in the plots below, you can see how much the results varied across different predicted worlds. And you can see that for some of our outcomes, the results were pretty consistent across imputed sets, while for other outcomes, the results varied importantly, meaning that we can't have as much certainty about the impact of the program on those 2 outcomes because of the missing data. And so we should be more careful when making recommendations about those outcomes. So just some takeaways. If you are dealing with social data, missing data is almost inevitable. And it gets worse with vulnerable populations. So I think the responsible thing to do is to make an effort to assess the damage that missing data can have on your ability to answer your original research questions. And multiple imputation provides a nice framework to do that. miceadds, Boruta, and randomForest packages in R can help you navigate some of the challenges if you're dealing with complex social data. And it is important to try to be aware and transparent about what you can and what you cannot learn from your data. If anyone has questions for me, or if you just want someone to vent with about your own missing data misadventures, feel free to reach me at mmd486@nyu.edu. Thank you.
Thank you very much for that talk. It was wonderful. And that's an example of finding someone at one of our events and they had to go and become a speaker. I think that is a wonderful thing when that happens. That was a great talk. I hope everyone enjoyed that.